The last of our basic techniques of integration is partial fractions. And before we go into that process, I need to go back. I think it'd be a good idea to go back and review some of the basic antiderivative rules that we have, or techniques that we have so far. Because each of these four, and then there are going to be a couple more we'll take a look at here in just a bit, each of these four is going to be the type of integral that you inherit from this partial fraction. Sometimes this is called partial fraction decomposition. We're going to take this larger expression, decompose it into a set of smaller expressions. And so understanding how each of these works, having these in your comfort zone is sort of important. So let's just go back and take a quick little brush through here. Each of these has a particular procedure. Notice this is for, the numerator is the same, 4, but notice this is x plus 1. This is x plus 1 quantity squared. This is x squared plus 1. These are different structures. They require different procedures. And then this is x squared plus 1 quantity squared. So each of these comes into play, and they're solved using a different procedure. And what I'll say is, for example, eventually we're going to get to the place where I'll say, this is a U substitution, or we're going to get to the place where this is tangent inverse form, or this is natural log form. So these have forms that they tend to match up with. And so that's the procedure. So we need to, again, let's review how to solve each of these. This first is straightforward. This is let U equal x plus 1, du equals dx, and the substitution is exact. This is the antiderivative. You can take this 4 and throw it out front. In each of these cases, you can throw this 4 out front if needed. But this is 1 over u du. This is the natural log form. And so it's not too hard to see that this is 4 times the natural log absolute u. And then 4 times natural log, let's go back to the original variable, x plus 1. And so it's not too hard to see. There's nothing magic about x plus 1. If this had been x minus 5, this would have been natural log absolute x minus 5. If this had been x plus 3, this would have been natural log x plus 3, absolute x plus 3. And notice, if there had been a 2x plus 1, this would have been 2x plus 1. The derivative would have been 2 dx, but then you move this to the other side of the equation, and now we have our 1 over a rule. So if there is a coefficient in front here, that just takes the form of the 1 over a rule. So what we can say is, this is the natural log form. Constant multiplier multiplies along. We have the 1 over a rule, and then we have the natural log of absolute 2x plus 1. And I would certainly permit you to go from here directly to the final result without needing to show any of this intervening work. If you need to show it in order to get it correctly, then you need to go ahead and show this work and do this work so that you can follow your own efforts. But just saying this is the natural log form going from here to here, and certainly if the coefficient is 1, this should be very straightforward. This is the natural log form. This is the natural log form. All right, the next piece. This is a calculus 1 integral, because we can rewrite this. We can put this 4 out front. This is x plus 1 to the negative 2. And we can let u equal x plus 1. du equals dx. The substitution is exact. So what do we have here? This is 4 antiderivative. This is u to the negative 2. And the negative exponent, this is just the power rule. The power rule says add 1 to the exponent, divide by the new exponent. So this is 4, add 1 to the exponent, so this is u to the negative 1, divide by negative 1. And so what do we have here? That's u to the negative 4, negative 1 in the denominator, U is, what is U? U is x plus 1, so this is x plus 1 to the negative 1, and you're out. So if it's second power, just do a U substitution, an ordinary garden variety calculus 1 U substitution. This is negative 4 x plus 1 to the negative 1 plus c, and you're out. Negative 4 here. All right, so if I have a linear expression squared, that becomes an ordinary U substitution, and use the ordinary power rule. All right. The next form is very straightforward because this is the tangent inverse form, right? This is tangent inverse, where U is equal to x and A is equal to 1. This is straightforward. This is constant multiplier. And then we have for tangent inverse, the tangent inverse form, remember that's 1 over A tangent inverse of U over A plus the constant, where in this case A is 1. So we have 1 over A is 1, tangent inverse U over A, that's x over 1, plus the constant, so that's 4 tangent inverse of x plus c. And so if you have x squared plus 1, or x squared plus 4, x squared plus 9, this is the tangent inverse form. All right? And then the last piece, this is excuse me. And so this is recall what we did with our trig substitution. We can rewrite this as this is x squared plus 1 square root, but a quantity to the second power we can rewrite as the square root to the fourth power, and that's an ordinary U substitution, right? I'm sorry, not a U substitution. That's a trig substitution where we have the square root of the sum of squares. Square root of the sum of squares. So that's square root x squared plus 1. That's x, that's 1. This is an ordinary, just go right down the line, trigonometric substitution. And so having a feel for how to work out each of these basic integrals, what now I hope are becoming basic integrals, is very key. So we're going to take this larger expression, break them down into smaller pieces, and then you need to know how to handle each of those smaller pieces. And so that's the process we're going to be going through. That's the introduction, and then what we'll do now is go through the details of the particulars of the partial fraction decomposition method.